I'm Pat Dugas. This screencast is about solving quadratic equations analytically through factoring. And by the end of this, you should be able to write quadratic equations in standard form and be able to solve some quadratic equations analytically by factoring. Let's look at some key concepts that are involved in factoring and being able to solve quadratics. First of all, the zero product property comes into play in a very important way. So if we have two numbers, let's call them A and B, that equal 0, then by the zero product property, either A must be 0 or B must be 0, or possibly both of them, because any number multiplied by 0 equals 0. So where this comes into play with the quadratic, let's say it's in the form of x minus p times quantity x minus q equals 0. Well, for that whole quadratic to be equal to 0, then either the first part, x minus p, or the second part, x minus q, must be 0, or possibly both of them. So if we can get it into that sort of form, then we have the solutions to the quadratic equation. Another super important concept in factoring is the idea of the distributive property. If I have something in the form of x minus p times quantity x minus q, and I distribute the terms using the distributive property of multiplication, x times x becomes x squared. Then I distribute that x term to the second term, the q. X times negative q becomes negative qx. Then I distribute the negative p to the x term. Negative p times x is negative px. And negative p times negative q becomes positive q. So understanding how to distribute and apply the distributive property to these binomial two-term expressions is very crucial. Another important concept is the idea of what's called the greatest common factor. And that's being able to pull something out that terms have in common. It is mathematically the largest term that divides into all parts of an expression. Also, a difference of perfect squares sometimes comes into play. You sometimes get quadratics that involve two perfect squares. For example, if I have something that's m squared minus n squared, using this idea of the distributive property, that can be factored into something that's m plus n times m minus n. This is the only case where the middle terms, this minus px and minus qx part, factor out. Because what happens if I were to distribute this, m times m is m squared, m times negative n is negative mn, but then I have an n times m, which cancels out the m times negative n, because negative mn plus mn is equal to 0. And then finally, if I distribute the n to the minus n, I get negative n squared. So let's look at an example of writing quadratics in standard form. Let's say we have an equation that is in standard form, and we know that x equals 1/2 and negative 5 are its roots. So let's write the pattern. X minus p times x minus q is equal to 0. We know that for something to have a root, that means that number makes it 0. That is the x, or horizontal intercept. So we write this in the form x minus p times quantity x minus q equals 0. So I'm going to replace the p with 1/2 and the q with negative 5. Now it is in the form x minus p times x minus q because we're told these are the roots. By the zero product property, x minus p equals 0 means that p, putting in a p for x, will make the whole thing 0. In other words, putting in a 1/2 for x will make this part 0. Putting in a negative 5 for x will make this part 0. So I can simplify that because x minus negative 5 is the same as x plus 5. Okay, so we're asked for this quadratic equation in standard form. So that means we need to go ahead and distribute. So that means we need to go ahead and distribute. X times x is x squared. X times 5 is 5x. So I've got an x squared plus 5x. Negative 1 times x is minus 1/2 x, or negative 1/2 x. Negative 1/2 times 5 is negative 5 over 2. Okay, we'll clean that up here in a second, but that's using the distributive property. And when we do that, that gives us x squared plus 9 over 2x minus 5 over 2 equals 0. We're combining those middle terms. Now, in standard form, there shouldn't be any fractions, so what we need to do is multiply both sides by 2, which is the denominator of 2 of the terms. There's nothing algebraically wrong with this, but to put it in an actual perfect standard form, we need to get rid of that. So that becomes 2x squared plus 9x minus 5 equals 0. And that is the quadratic equation in standard form that has those two numbers as its roots. Now, graphically, what that means is this equation has intercepts at x equals 1/2 and x equals -5. We also know it's an upward-facing parabola because the 2 is positive, the a term, and we know it has a y-intercept at -5, that's the c term, and halfway between these 2 points is its axis of symmetry at -b over 2a, -9 over 4, which is right about here. So we know there's an axis, even though I haven't drawn this perfectly. We know our parabola looks something like this. So some quadratics can be solved by factoring out their greatest common factor. What's the largest term that they have in common that divides into all the parts? So if we look at 9y squared and 3y and see what they have in common, well, they both have at least one y to the first power, and 9 is a multiple of 3. So what they have in common is 3y. Okay? So if we take out that 3y from both the terms, what we have is if we divide 3y into 9y squared, we get 3y. So 3y times 3y becomes 9y squared. So we factored out the 3y. If we take out a 3y out of 3y, we're just left with 1. So this 9y squared plus 3y equals 0 can be written by factoring out a 3y like this. Using the distributive property in reverse, we're going to group this 3y and this 1 together because 3y times 3y plus 3y times 1 is the same as 3y times 3y plus 1. It's the distributive property in reverse. Now we use the zero product property. Either this first part is equal to 0 or this second part is equal to 0. So either 3y equals 0, and we can solve that out algebraically, or 3y plus 1 is equal to 0. If either of those things is true, then that's a solution to this equation. So 3y equals 0, we're going to divide both sides by 3, and we get y equals 0 as one of the solutions. Here in the second part, we have to subtract 1 from both sides using the subtraction property of equality. So we get 3y equals -1. And then we use division property of equality, dividing by 3. And so we get y equals -1/3. Both those are the solutions to the original equation, and both of those will work. Again, in all these screencasts, I typically skip the checking step. It's absolutely essential that you try to check your work and make sure that both these solutions do indeed work. If you have a situation that involves perfect squares, and here's one of them, y squared equals 36. Well, we know that y squared is a perfect square of y. 36 is also a perfect square of 6. So it's a perfect candidate for factoring with perfect squares. First thing we have to do, though, is take that and use the subtraction property of equality and subtract 36 from both sides. So then we get it into a more standard form. Y squared minus 36 equals 0. Now this fits into a difference of perfect squares. Y squared minus quantity 6 squared equals 0. 6 squared equals 36. So now I have two perfect squares, but crucially, it's in the form of a squared minus b squared, or m squared minus n squared, as I used in my example. And so this can be factored out into a difference of perfect squares as y plus 6 times y minus 6. Let's quickly check our work here. If I distribute y times y, I get y squared. Y times -6 is -6y. 6 times y is positive 6y, so those middle terms in this cancel out. And our last term is 6 times -6, -36. So y squared minus 36 equals 0 is correct. Using the zero product property, either y plus 6 is equal to 0 or y minus 6 is equal to 0. So in the first case, I'm going to use subtraction property of equality and subtract 6. In the second case, I'm going to use the addition property of equality and add 6. And so either y equals negative 6 or y equals 6 are the solutions to this equation. In this screencast, we began the factoring of quadratics using analytic techniques.